coordinate systems. So with a vector being a quantity that has a direction, and directions being something that we can specify based on a coordinate system, we want to make sure we have a clear understanding of what exactly a coordinate system is. But not only just the most common type of coordinate system, the rectangular coordinate system, we want to make sure we understand in general how different coordinate systems work and how vectors are defined and represented in different coordinate systems. Okay, so fundamentally what a coordinate system is it's a way of mapping out the location of points in space around us. That's what a coordinate system is. So the idea is, in general, let's say you have a room or a shop or a machine, something like that. Well, you're going to define a point, maybe in the center of the room or just based on some starting location or whatnot. But you're going to define a point that we call the origin. And then with this, the location of points in space are mapped out relative to this origin point. But the way that they're mapped out is based on the coordinate system that's used. There's different ways you can map out the location of points around an origin point. Okay, but now, in the most general sense, space around us is three-dimensional. Three-dimensional. There are certain systems that only require us to map out one-dimensional space, maybe like a conveyor belt, the location along a conveyor belt, for example. There's other scenarios where we only need to map out space in 2 dimensions, but in the most general case, space around us is three-dimensional. So, but what exactly does this term dimensional mean? What are we talking about? Well, the idea is when you think about the phenomena around us that we can measure, like temperature, time, weight, length, space, locations in space. Length measurements or locations in space measurements around us is unique from time and temperature and weight, in the sense that, if you have some system like a car on a racetrack or a machine component turning, etc., to track time, to specify the time of something, you only need one parameter. To fully specify the time, like 7.4 seconds. You need one parameter. That's it. And it's the same idea with temperature. To fully specify the temperature of something at a certain location or whatnot, you only need one parameter, 112 degrees Fahrenheit. One parameter. And so quantities like time and temperature are one-dimensional. To fully describe these phenomena, you need one parameter. Okay, but when you think about it, space around us is unique in that to fully specify a location in space relative to some origin point, in the most general case, where we're not constrained along a conveyor belt or to some sort of a plane, something like that, in the most general case, you're going to need 3 parameters to specify all potential locations around an origin point. You have to have 3 parameters. There's no other way to do it. Like it's not possible to use less than 3 parameters to fully specify locations in space around an origin point. And that's why space around us, we call it three-dimensional. Okay, so let's think about, we're in some room here, some three-dimensional space. Let me try and indicate that we're in a 3D space here. Okay, and we're going to specify at the center of the room an origin point. Okay, and so to specify the location of any point in this 3D space relative to the origin, what we do is we list 3 parameters in a group like this, where in general A, B, and C are any real number from negative infinity to infinity. And what these parameters, what we call coordinates, correspond to is some amount of span in space. And I'm saying span, not length, because there's 2 ways you can specify an amount of distance between points in space. You could do this with a linear parameter, so that would correspond to a length, right? The distance between points, right? What is the straight line distance between these 2 points? Or if a curve connects the 2 points, What's the total length of this curve? Okay, but another way that we can specify sort of a span between 2 points is with an angular parameter. We can say what's the angle between these 2 points. Okay, and so with that, then the idea is, if you're going to make a coordinate system for 3D space, you're going to need 3 parameters. 2D space, you're going to need 2 parameters. 1D space, you're going to need 1 parameter, which we call coordinates. Well, you can create any kind of coordinate system you want. Okay, but when you do this, the parameters that you're going to use to define the coordinate system are going to be either linear or angular. For a 3-dimensional coordinate system, you could have all 3 be linear, or you could have all 3 be angular, or you could have some mixture of both. But no matter what, you're going to have 3 parameters for a 3-dimensional coordinate system. No matter what, you're going to have 2 parameters for a 2-dimensional coordinate system. And then, obviously, 1 parameter for a 1-dimensional coordinate system. And again, these spatial parameters specifying it's a span moved in space can either be linear or angular. It's your choice. Okay, now, but what do these parameters correspond to? So if I have, A, B, and C here, let's say I have, these could be any real number, 3, -1, 7. Well, what does this mean? How can I locate what, this is some point, apparently, relative to the origin, some point, maybe, is it this point? What does this mean? Well, what these parameters correspond to is the amount that you need to move either along or parallel to the respective coordinate axis that parameter is associated with. And this coordinate axis is based on what coordinate system you're using. So what's a coordinate axis? Well, a coordinate axis is, so if we leave 3D space, okay, let's say we're going to make a 1-dimensional coordinate system. Okay, in that case, we just need 1 parameter to specify any location relative to an origin point. Okay, let's say the parameter is going to be a linear parameter. It could be linear or angular. Let's think about the types of 1-dimensional coordinate systems we could create with a linear parameter. Well, we could, the simplest type would be some sort of a straight line. Okay, and so this here is a coordinate axis. I've got a coordinate axis, and the next step is I apply a grade or a scale to it. Let's say I'll do evenly spaced tick marks. Okay, this is 1, 2, 3, 4. Okay, and with that, if I specify a 1 parameter from -infinity to infinity, that's going to specify the location on this line, 2.32. That's around, right here. Okay, but to think about this generally, the straight line doesn't have to be horizontal. It could be tilted. Okay, but then furthermore, it doesn't even have to be a straight line, right? I could do whatever. So this is 0, -1. Okay, specify parameter, and that fully constrains the location along this coordinate axis here. Okay, and so what you can see is that a coordinate axis, if we come back to 3D space, is going to be the 1-dimensional coordinate axis system that corresponds to this parameter, and this parameter, and this parameter. This will be the A coordinate axis, then the B coordinate axis, the C coordinate axis. So let's say this was going to be a 3-dimensional coordinate system with all linear parameters. Then in general, the idea is maybe this is the A coordinate axis, and this is the B coordinate axis, and this is the C coordinate axis. This is like, I'm trying to keep this as general as possible. Yes, you could obviously make any one of these straight lines, but in general, this is the idea. It's just some completely general 1-dimensional system. So if we said this is positive A, this is positive B, this is positive C, we apply a scale. Okay, then the point P relative to this coordinate system would be, we go +3 in the A, then we go -1 parallel to B. So it's kind of hard to see here, but maybe that would be something like this. And then 7 parallel to C. 1, 2, 3, 4, 5, 6, 7. So we'd be over here. That would be point P. Now, this was hard to plot, and the reason is because there's no minor axes drawn here. So you have coordinate axes, but what you have is major and minor coordinate axes. The major axes pass through the origin of the coordinate system. Okay, and the minor axes are off of the origin, but parallel to the major axis. And they're usually more faded than the major axis. And the point of the minor axes is that, because remember, to plot a point relative to a coordinate system, you're moving either along that major coordinate axis or parallel to it. So that's what the minor axes are there for. It helps you to move parallel to the major axis. So, in other words, a minor axis corresponding to C would be something maybe like this. And you draw a bunch of those. And then you draw some parallel to A. Some parallel to B. And so let's see if I got that right. So 3 in the A, 1, 2, 3. Then minus 1 in the B, which was over here. You see, if this is B, this is positive B, so I need to do like this. You see, this is minus 1 in the B right here. And then 7 in the C, let's see, here's C, so you go 1 parallel to this. 1, 2, 3, 4, 5. So that was about right. Okay, so that's the idea. Okay, but now what about an angular parameter, an angular coordinate axis? Okay, so the way this works is, so let's say one of these parameters here, maybe the first parameter was an angle, theta. Well, the way it works is the coordinate axis for theta is going to be some straight line that goes through the origin. It doesn't pass all the way through like this. It just comes out in one direction from the origin, and it's oriented anywhere you want in 3D space. You specify its orientation, say like that. Okay? And it's just fixed there in this orientation. That is the coordinate axis for theta. Okay? Now, what you also need to do though is specify in which direction is theta positive. So is this positive theta or is this positive theta? Let's say we're saying that this is positive theta. All right, and so with that then, the way it works is, if you've got a point anywhere in 3D space, then its theta coordinate is based on it. So you connect that point to the origin with a straight line. And now these two lines here are going to have an angle between them, and that's theta. Now, if you specified that theta was positive in the other direction, then this would be the coordinate, this angle. And that's it. That's in general the way that angular parameters and angular coordinate axes work. Now, we're going to see, in certain coordinate systems, like cylindrical, the coordinate axis for an angular parameter is constrained to like this horizontal XY plane, and then it's based on the first dimension. It's just some angle in the horizontal plane. It has to be. So you can set it up and constrain it however you want. But in complete general, this is how it's going to work. You're going to orient some straight line going out of one direction from the origin and constrain it to some point in space. That's the axis of the angle parameter. You define what direction is a positive angle. It's going to be one of two directions, and that's it. You're done. Because no matter where some point is, even if it's on the axis, you can draw a straight line from the origin to that point, and there's going to be an angle between the reference axis and that straight line to the point. And that's the angle. Okay, now, there's some coordinate systems where you'll have two angular parameters. So we could have another angular parameter. That would be something like, orient this. You can't orient it on the same exact direction as the theta parameter, but, anywhere else, maybe like this. Okay, let's say this is alpha, and this is the positive alpha direction. So there's another angular coordinate for P. Now, I mentioned that you can have three angular parameters. However, one thing to note is that we couldn't define a third angular parameter that has an axis also going through the origin. That wouldn't work. We'd have to, that wouldn't constrain P. We'd have to use some axis that's off the origin, but we're not going into that much detail about coordinate systems here. Okay, so if you're only going to have an angular parameter that's defined this way with a coordinate axis that goes through the origin, then at most you can have two angular parameters, but from there you're going to need one linear parameter. Okay, now there's a few more things we need to go over before we start talking about some specific types of coordinate systems. So okay, let's put back in. Here's just a general linear axis, A, then another linear axis, B, and then maybe C is an angular axis. Okay, well, first of all, just note that the most fundamental purpose and use of a coordinate system is for mapping out points in space, 1D, 2D, or 3D space around us. Okay, but however, as we all know, we do use coordinate systems as a tool for visualizing relationships between variables that don't necessarily have anything to do with 3D space, right? We do this all the time. So maybe we're running a shipping business, shipping packages, and we're getting data points based on, so a package comes in, you have the weight of the package, the size of the package, its volume, and then the cost to ship the package, the price. So we can get a bunch of data points. And so once we have a bunch of data points, 100 data points, whatever, one way we can visualize how these variables are related to one another is we can plot them on a coordinate system. And then if we have enough data points, we can connect the dots to get a full picture. And so what we do is we treat these variables like they're coordinate directions. And we go a certain amount along the w-axis, a certain amount along the v-axis, a certain amount along the p-axis. We just replace A, B, and C with W, V, and P. Now, we typically view relationships between variables on a rectangular coordinate system, which we'll talk about in a second, but you can plot relations like this, a set of data points on any coordinate system you want. Okay, so just note that. It can be confusing when you think about a price vector, the direction of, how certain variables have directions. Weight has a direction, volume has a direction. That's just because we're using coordinate systems, which are north, south, east, west. There are directions within coordinate systems. They're related to mapping space around us. We use that as a graphical tool for visualizing relationships between variables, even though weight and volume and price have nothing to do with actual space or directions. Okay, now what I've also been doing here is applying a scale or gradation to each coordinate axis. Okay, now if the coordinate system you're using applies actually to space, like space around us, 1D or 2D or 3D space, then most likely you're going to have all of the axes scaled the same way with the same gradation of tick marks, these evenly spaced tick marks. This would be in feet. This would be in feet. However, you can think about how if you were plotting the relationship between different variables, if this was pressure, this was velocity, this was energy, or weight, volume, price, then you might want to scale the axes differently. And you're absolutely allowed to do that. You can scale coordinate axes however you want. You can apply tick marks however you want. You don't have to have evenly spaced tick marks if you don't want. You can do whatever you want. You could have one of these axes logarithmically scaled, but leave the other one linearly scaled with evenly spaced tick marks, or whatever you want. It's up to you. Okay, now, but when it comes to the gradation and scaling of an angular axis, that's kind of a little bit different because in general, you're going to be using degrees or radians, and those angles are defined based on, degree. A degree is you separate a full rotation into 360 equal spaces, and each one of those spaces is a degree. That's the definition of a degree. It's a similar idea with a radian. So, but I mean, if you wanted to, you could scale in terms of how the scaling of a full rotation is spaced out. You could technically do whatever you want. I guess you have to make up your own type of angle, but technically you could if you wanted to. Okay, now the last thing to talk about before we look at some specific types of coordinate systems is, so just note that the idea of what a one-dimensional coordinate system could be. You could have a straight line that's angled in any way. You could have a curved line. There's different ways of thinking about something being one-dimensional, and it's the same idea with 2 dimensions. So remember, a plane, yes, a plane is 2-dimensional, and that's the classic figure that we think about when we think about something 2-dimensional. Okay. However, just remember that there's different systems that are 2-dimensional outside of just a plane. Any surface is a 2-dimensional system. The surface of a sphere, for example. You could have a 2D coordinate system that locates all potential points on the surface of a sphere. You just need 2 parameters. You give 2 parameters, and you're anywhere on that spherical surface. Something like this. This surface here. You could come up with a coordinate system that uses 2 parameters because a surface is 2-dimensional, and you can locate any point on this surface. Okay, so just keep in mind the general idea of what can be 1-dimensional and 2-dimensional. And then obviously, 3-dimensional is just anything that requires all 3 dimensions, like something solid or a volume. Okay, now let's talk about 3 of the most commonly used types of coordinate systems, which are the rectangular, the cylindrical, and the spherical coordinate systems. We're looking at all 3 of these coordinate systems from a 3-dimensional perspective. However, you can use a rectangular coordinate system in 2 dimensions if you want to map out points in a plane. You can also use a cylindrical coordinate system in 2 dimensions if you want. This is called we call this a polar coordinate system. And that also will map out all points in a plane. And spherical you can apply in 2 dimensions as well to map out all the positions on the surface of a sphere. Okay, but let's think about we're in a room or like a machine, some system here, some 3-dimensional system, 3D space, and we're thinking about a point at the middle of the room that we're going to call the origin. So all the coordinate systems we're going to talk about here are going to be centered about this same origin point. All right. A rectangular coordinate system, the fundamental key features that make up a rectangular coordinate system are that the coordinate axes, all of the coordinate axes are straight line linear coordinate axes, no angular axes. So it's all straight line linear coordinate axes. And then furthermore, all the coordinate axes are perpendicular to one another. If you have those 2 criteria, then you have a rectangular coordinate system. All right, so here's a 3-dimensional rectangular coordinate system. So you have 3 coordinate axes for the 3 dimensions. You can see each one of the axes are straight lines, but then furthermore, they're all perpendicular to one another. Okay, now, but it's important to note that, so the most common way you'll see a rectangular coordinate system is, so the variables for the coordinate axes for any rectangular coordinate system, the first 2 dimensions are going to be x and y, and then if you go to 3 dimensions, the 3rd dimension is going to be z. And most commonly, when you have a rectangular coordinate system like this, you're going to have the z-axis vertical pointing straight up and down, with the x and y axes making up this horizontal plane, the xy plane, right? Anywhere where z is equal to 0, you're in this xy plane. This is the most common way you'll see a 3D rectangular coordinate system. However, it's important to note that It's not a requirement for a rectangular or a Cartesian coordinate system that you have the z-axis straight up and down. This here, this is still a rectangular coordinate system. And why is that? Well, because the axes are all straight lines, the coordinate axes, and they're all perpendicular to one another. You can have a rectangular coordinate system oriented however you want. It doesn't matter. You know, we could rotate this into the page. It's hard to show that, but we could orient this however we want. As long as the coordinate axes are all straight lines and they're all perpendicular to one another, then it's rectangular. Okay, so let's see, x. Okay, and so to specify a point within this space, you just provide an x parameter, a y parameter, and a z parameter, where x, y, and z are just any real number from negative infinity to infinity, unless the certain system requires you to put a restraint on, you know, x can only be so big because the room is only so big, etc. But, you know, in general, x, y, and z could be any real number. And so if we wanted to specify point P at 3, -2, 5, then what that means is we go start at the origin and go 3 units along or parallel to the x-axis, then 2 units along or parallel to in the negative y direction, and then 5 units parallel to the positive z direction. So, okay, +3 in the x, we get to here. Okay, -2 in the y. So now we're here. So we went 3 in the x, -2 in the y, and now we need to go 5 in the z. So let's see. And that's it. There's point P. +3, -2 in the y, 5 in the z. And so you see with that, you can locate any point you want in this 3D space. Now again, if you want to use a Cartesian coordinate system in 2 dimensions, then you're just going to have 2 straight line axes that are perpendicular to one another. But you could orient this however you want. You could tilt this, it doesn't matter. Okay, the first coordinate is going to be x, second coordinate y, and you just specify a point. -3, -2. 1, 2, 3, 1, 2. There we go. Okay, now let's look at a cylindrical coordinate system. So we've got this same room here with this same origin point in the middle. Okay, and the idea is with a cylindrical coordinate system, you would start by specifying a plane that's centered at the origin. And so, you know, in actuality, we could have started with the rectangular coordinate system. We could have started this way as well. Since a rectangular coordinate system can be oriented however you want, we could have said the same thing, how we would start a rectangular coordinate system by specifying a plane that's centered at the origin. So something like this, for example. Okay, and so like the idea would be with a Cartesian coordinate system, once you have this plane, then you have the x and the y axes are contained within this plane, oriented however you want. Maybe that's the x-axis. And then, but the y-axis would have to be perpendicular to this line, right, for it to be rectangular or Cartesian. So that's x, that's y, and then the z-axis would be perpendicular to the plane. So you can see, but everything's perpendicular here. Okay, but now with a cylindrical coordinate system, we start by specifying a plane. Okay, now similar to rectangular, we are going to have a linear axis that's a straight line that's perpendicular to the plane. Like shown here, this is one of the coordinate axes. This is the z-axis. So we're going to have r, theta, and z. 2 linear axes and an angular axis. Okay, but in the third axis, this is z. All right, now r and theta, what r and theta are going to do is they're going to specify a unique location within this plane. So what r is going to be is r is going to be, you're going to be some fixed radial distance from this origin point within this plane. So some fixed distance from the origin. That's the tick marks. So if your r is equal to 1 away, then you're on some circle that's 1 unit away from the origin in any direction. If you're at r is equal to 2, you're on some circle that's of radius 2 about centered on the origin. Okay, and then what theta is going to do is theta is going to be, you're going to, the theta axis is going to be some line within the plane as well. So let's say this is, and you can put theta wherever you want. Let's say this is theta. Okay, and the convention is going to be that whatever you define to be positive z, you know, it could be above the plane, but whatever you define to be positive z, then what you do is you look down at the plane from the positive z direction, and you look at the theta axis, and then counterclockwise is going to be positive. So in that case, this would be positive theta. And then r, you would have these circles. So this is, you'd be at r is equal to 1, 2, 3, 4. Right? That's like the tick marks for r. That's the r axis. This is like the r axis, these circles. So with r and theta, with r, you're some fixed distance on some fixed circle away from the origin. Then theta fixes your location on that circle. So now you're fixed in this plane. And then z is just how much you go above, linearly above or below the plane. Okay, now, but what's commonly done is what you'll see is in a lot of cases for a coordinate system that other than rectangular, you'll often see like a rectangular coordinate system put in the background faded as a reference. So if we do that here, okay, so here's a rectangular coordinate system in the background. Okay, now, so when you're going to line up cylindrical coordinates with rectangular, and when I say line up, the idea is you want to line them up in a way that's going to be consistent with the formulas that are used to convert between coordinate systems. And what converting between coordinate systems means is that if you have a point in space, okay, well, let's think about how points in space, points on a machine, any locations on a map, whatever, they're independent of the coordinate system. They don't know that a coordinate system's there. If you change coordinate systems, the point or like the building or the machine component doesn't change location or shape, right? And so the idea is when we're converting between coordinate systems, what we're doing is if we start with one coordinate system, like a rectangular, and this has coordinates x, y, and z, and then we switch coordinates to like cylindrical, then we're wanting to know, okay, what is the corresponding r, theta, and z value that will map out this exact same location in space? That's what converting between coordinate systems is all about. That's what we're talking about when we say converting. Okay, and so now if you want to be consistent with the formulas you're going to see for converting between rectangular and cylindrical, then this is how you want to line up the two systems. Okay, the way it works is that the xy plane, anywhere where z is equal to 0, that's where the plane, the r theta plane of the cylindrical coordinate system is going to line up with. That's going to be the same plane. So we used r and theta to constrain a point within that plane. Okay, well that plane is, in terms of the rectangular coordinate system, we're going to line up the xy plane with that plane. And therefore, what happens is that the z-axes line up. Because remember, with cylindrical, we just had a straight line z-axis perpendicular to the plane. So the z-axes are going to be exactly the same. So in that sense, what you can think about is when you're converting between rectangular and cylindrical, the z coordinate is going to be the same for both systems if you use this convention to line the two up. Okay, now, so with that then, if we think about the xy plane, then since the cylindrical plane and the XY plane are lined up, then the R axis, the R coordinate axis is going to be circles that go through. So here's one tick mark away from the origin of the X axis. Here's one tick mark away from the origin of the Y axis. So we're going to have circles that go through these common tick marks, right? Like this. So there's the R axis. Okay, so we've got the Z axis, we've got the R axis. Now, for the theta axis, the convention is you line that up with positive X. So the theta axis is going to go here. There's theta. And now, if we look down the positive Z axis, we can see that this is counterclockwise. So there's theta. And that's it. That's how you line them up. So we've got R, theta, and Z. And we have X, Y, and Z. And when they're lined up this way, you can use the conversion formulas to convert between the two. All right, so we can go ahead and derive these conversion formulas. So again, what we're doing is we've got some point in space, and we want to be able to describe that point with either R theta Z or with X, Y, Z, that exact same location in space. If we have R theta Z, how do we get the corresponding X, Y, Z coordinates and vice versa? Okay, well, again, the Z coordinates are going to be the same. If you've got a point in space, okay, and then on the origin, you've got a cylindrical coordinate system overlaid on top of a rectangular coordinate system in this orientation that we talked about, where the two horizontal planes matched up and the theta coordinate axis aligned with the positive direction of the X axis, then in that case, the Z coordinates for both coordinate systems are going to be exactly the same. So Z is going to equal to Z. And so with that, then what you can see is all we need to do is figure out how R, theta, X, and Y are related. Or in other words, the point within the plane is all we need to figure out conversion formulas for. Okay, so with that, let's look at this in 2 dimensions. Let's look at a polar coordinate system overlaid over a 2-dimensional rectangular coordinate system. Okay, so here's the positive X axis. So there's theta, okay, and then R is just some fixed distance from the origin within the plane. So if we pick some random point, so let me go ahead and let's pick a point here. So this point has an R value, it has a theta value, and it also has a X and Y value. Okay, well, we can use the definition of trigonometric functions to relate X, Y, R, and theta, because trig functions are defined for theta going over a full rotation. And they honor the sign of X and Y. If X is negative, the trig functions will take that into account. And it's same idea if Y is negative. But R is always positive in all circumstances, which is the case. That's what we're saying here with these polar coordinates. So with using trig functions, we know that cosine theta, in general, for a full rotation, like this applies if theta is greater than 90, if theta is in the third quadrant, fourth quadrant, etc. Cosine theta is adjacent over hypotenuse, okay? And sine theta is opposite over hypotenuse. Okay, so with that, we can see that X is equal to R cosine theta. So that's how you can, if you have R and theta, you can get the X coordinate of a point. And if you have R and theta, you can also get the Y coordinate of a point. Okay, and so this is how, if you have R and theta, if you're in cylindrical coordinates, you can convert to rectangular, because then we know just Z is equal to Z. So there you go. Okay, now, but what about if you have rectangular and you want to convert to polar? Well, we can use the Pythagorean theorem to relate x and y to r. So since x squared plus y squared is equal to r squared, then the principal square root of x squared plus y squared is going to be equal to r. Okay, now to relate theta to x and y, we can use the relation that tangent of theta is equal to y over x. And there we go. But then we also have z is equal to z. So here you can convert from rectangular to polar, or rectangular to cylindrical. Now, if you're trying to get theta and you have y and x, what you're going to have to do is when you take the inverse tangent of both sides, there's going to be two options for what theta could be. Two options from 0 to 360. So you're going to have to use the information you have to pick the correct theta. Remember from trigonometry, if you just use inverse tangent, it's going to give you a value between minus 90 and 90 degrees. But you have to look at the big picture and pick the theta that corresponds to your problem. Okay, but now let's plot a point. Let's plot the point for negative 135 degrees, or you could do that in radians, whatever you want, and minus 2. Okay, so we've got r is equal to 4, 1, 2, 3, 4. So we're somewhere on this r is equal to 4 circle. So there's negative 90, and then 135 is going to be right in the middle between, this is negative 180, so 135 is going to be, so 1, 2, 3, 4, about right in here. Okay, so now we're at this point, and from there we go minus 2 in the z. So let's see, we've got 1, 2. There's minus 2, so parallel to that r-axis, and there we go. There's point P. Okay, now similar to how we could take rectangular coordinates from 3 to 2 dimensions, we can do the same thing with cylindrical coordinates. Now, just to note though, with rectangular, we had x, y, and z. Well, in general, you can take any 3D coordinate system and pick any of the two of the three variables to look at two-dimensionally. But in the case of rectangular, no matter what you pick, x, y, x, z, whatever, you're going to be looking at a plane. You're going to be mapping out all points in a plane. Okay, but now if we think about cylindrical, we've got r, theta, and z. Well, if we choose just r and theta, then the result is going to be we're going to be mapping out points in a plane, just like with rectangular. Okay, if we keep the x and y rectangular axes in the background, then you can see, okay, in a plane here, we've got the r-axis, and then we would use the positive x-axis for the theta coordinate axis. So this would be theta, like that. And this would be r. Okay, so you can see you can map out all points in a plane with r and theta. Okay, but what you can think about is we could choose another pair of these coordinates to make a two-dimensional coordinate system. So if we used theta and z, then we could map out all the points on the surface of a cylinder of whatever radius we choose. Choose a radius, and then with that radius fixed, then all pairs of theta and z map out the surface on a cylinder that extends infinitely vertically or up and down. So you pick a constant r value, let's say r is equal to 3. Okay, and now with r is equal to 3 fixed, all combinations of theta and z will give you every point on the surface of a cylinder like this that extends infinitely up and down. Okay, but we could also think about, well, what happens if we used r and z? Do we get some sort of unique two-dimensional mapping? But unfortunately, that's not the case. You just end up mapping out a plane again, just like you did for r and theta. Okay, but now maybe it's like a unique way of mapping out a plane, but actually, okay, if we take a look, the idea is if we think about a fixed theta value, so somewhere like this, maybe. All right, so we're fixed at this theta. Now, r can vary to be whatever we want, and z can vary to be whatever we want. Okay, so there's the plane, but what are we doing here? This is just like a Cartesian coordinate system. It's a horizontal dimension and then followed by a vertical dimension. So, but you do get a unique type of mapping if you think about using a theta and z, unique type of two-dimensional mapping. All right, now let's take a look at spherical coordinates. So we're back to our empty room. We removed all of the coordinate systems, and we're just left with an origin point at the middle. Now we're going to add a spherical coordinate system. So the three parameters with a spherical coordinate system are you have rho, theta, and psi. Okay, you have two angular parameters and a linear parameter. The linear parameter is similar to r for cylindrical in that we're going to be a fixed distance from the origin, but in this case, it's a fixed distance in any direction, which means we're going to be on the surface of a sphere. Each tick mark is going to be like a sphere. So, like this. So, here's would be rho is equal to 1, and then this would be, I have this spaced out, this would be 3 tick marks, then 5 tick marks, then 7 tick marks, because it's hard to see. If you put too many spheres, it's hard to see, but if rho is equal to 3, then we're somewhere on this sphere, anywhere in 3D space. Okay, now for theta and psi, you can orient these coordinate axes however you want. However, you just want to make them perpendicular to one another. So we can orient the theta axis wherever, maybe here, and then just make psi perpendicular to this, like that or like that. I mean, just as long as it's perpendicular. Okay, then just define the positive directions for the angles, and that's it. This is in general how a spherical coordinate system is set up. Now notice that in terms of like orienting this in different ways, well, a sphere is symmetrical in all directions, so there's no orienting these spheres differently. You're just going to be reorienting the theta and psi axes. Okay, but now let's go ahead and line this up with a rectangular coordinate system. Okay, so here's the spheres, and you can see that the spheres are going to cross. Like, okay, r or rho is equal to 1, so we've got rho, theta, and psi. Rho is equal to 1 is going to, the sphere is going to cross through x is equal to 1, y is equal to 1, and z is equal to 1. You're 1 unit from the origin in all directions. Okay, same idea with rho is equal to 3. You're crossing through all of the 3 tick marks. Okay, now the convention is the way you want to line these up just to be in coordination with all of the conversion formulas you'll find in textbooks and online. I mean, you could line them up however you want and do the conversion formulas yourself. But in general, the way you're going to want to line it up is to just, if you want to be in synchrony with the standard way it's done, is you're going to put the theta axis in line with the positive x-axis. Okay, so there's the theta axis. And then looking down positive z, whatever's counterclockwise is going to be the positive direction. Okay, then the psi axis is going to be in line with positive z. That's the convention. And the idea is you first specify a rho, then you specify a theta, and so with that, you're going to be on one side of the z-axis. You'll be either over here or you'll be over here once you specify a rho and a theta. And what you do is then psi is, you just think about it as some angle between 0 and 180 degrees, or 0 and pi. That's all you're going to need. But I mean, you could still specify a psi, any psi you want, any theta you want, just like you could do a negative rho or a negative r, and you could still interpret what that means. But in general, like it would be, it's redundant. It's technically redundant to, in this case, to have a, like you don't need any negative rows, right? You don't have to have negative rows. Just like with cylindrical, you don't have to have negative R's. You can still specify it, but you don't have to have it. Okay, same idea here. You don't have to have angles less than 0 or greater than 180. Okay, because the idea is, again, you specify a row, you specify theta, so you're somewhere over here, or you're on one side of the z-axis, and then, so let's say we're over here, kind of in the back. Well, then psi is going to be, is measured this way, right? It's going to be between 0 and 180. So, okay, let's say we've got the point 3, 135 degrees, 30 degrees. You can do this in radians as well. So in this case, we've got 1, 2, 3. And so rho is equal to 3. Now we go theta is 135. So there's 90. There's 180. So we're somewhere over here. We're on rho is equal to 3. And now we go 30 degrees. So this is 45. So about here. So let's see. Like that. There's P. You see, we went, let me draw this out, make sure it's accurate. So we went, there's theta is equal to 135, and there's psi is equal to 30, and then we're on rho is equal to 3. So we're 1, 2, 3, this spherical surface, like so, right around there. You see, there's 135, there's 30, and there's, now we can go ahead and derive the conversion formulas. What we'll do is we'll derive the conversion from rectangular to spherical, but then once you have that, then you could use the conversion formulas for cylindrical to spherical to convert between either of the three. So, okay, the way we're going to do this is, so, okay, let me put all this back. Here's the rectangular. All right, now we've got, you can overlay it however you want and derive these formulas using the technique we're about to show however you want. But again, if you want to be in line with what you're going to find online and in the textbooks and whatnot, then what they'll do is they'll put the theta axis in line with positive x and the psi axis in line with positive z. And there is no orientation regarding the spheres. All right, so now, okay, so we've got some random point. Let's say it's in the, let's say it's down here, kind of in the back, just to make this as general as possible. Okay, so this is point P. This is, let me try and draw this clear. So we've got that, and then, so, yeah, you can get a better sense of where we are. There's point P. Okay, and so with that then, in spherical, the coordinates are going to be, you've got, there's rho, okay, there is theta, and there is psi. Okay, so what we can do is, to relate the rectangular and the spherical coordinates, we can write this as R. Okay, this is, so this would be the R in cylindrical, right? We're in the XY plane, the horizontal plane, so this would correspond to the R in cylindrical, right? And so with that then, what we can see is we can draw in the, here's the X coordinate, and here's the Y coordinate. Okay, we can start with the same relation we used for cylindrical, in that X is equal to R cosine theta, and Y is equal to R sine theta. Okay, but what is r? There's no r. When we're converting between spherical and rectangular, there's no r. Well, okay, we can get r because, okay, it's kind of hard to see, but let's say hypothetically P was over here. And so here's the rho, and then the R would be, you're somewhere here in the XY plane, so this would be the R. Okay, but we can draw the R up here as well. Okay, this is the rho, and in this case, this would be the psi. Okay, so you could say sine of psi is equal to opposite over hypotenuse, r over rho. So it would be sine of psi is equal to r over rho. Now, with this, to do this though, this works fine as long as psi is between 0 and 180, because sine is positive between 0 and 180. But if you allow psi to go past 180, then you have to be careful, because then you're going to get a negative value for sine of psi, but r and rho can't be negative, so you have to be careful there. But again, the standard way that this is set up is that theta can be any angle between 0 and 360, 0 and 2 pi, or whatever, even negative angles, whatever. But you just make psi go between 0 and pi, 0 and 180. And in that case, this conversion formula is fine for all circumstances. But if you wanted to allow psi to go beyond 180, I mean, you could derive it however you want. You just have to adjust the formulas. So, okay. With that, then, we can see that, coming back to the original point, we can say that, so sine of psi, again, is r over rho. So in that case, we've got r is equal to rho sine of psi, and there we go. So now we can say that x is equal to rho cosine theta sine psi, and y is equal to rho sine theta cosine psi. And there we go. But now, what about z? So here is, you can see here is z. Well, we could use trigonometry once again using psi, in that cosine of psi is adjacent over hypotenuse. So it's kind of hard to see here. Let me put another point back. So we've got, let me put another point back. So, okay, there's rho r psi, and then this is z, right? Okay, cosine psi is equal to z over rho. Okay, but now this will work though, because cosine is going to change to negative in the second quadrant, so you're going to get you would get a negative z value like you're supposed to if psi is greater than 180 or greater than 90. And actually, this would work if psi was greater than 180. This would actually work as well. You wouldn't have to make any adjustments like you would for sine. So we can say that cosine of psi is equal to z over rho. So we've got z is equal to rho cosine of psi. And there we go.